Alright, in this video we're going to do questions 60 to 62 in the June 2013 Chemistry Regents exam. Alright, so we got a couple of gases here in cylinder A and cylinder B, so it tells us that in cylinder A we have hydrogen gas, and in cylinder B we have methane gas. Alright, so the two cylinders, the first thing it asks us is what is the total number of gas molecules in each of these. So the key here is we have the pressure, the volume, and the temperature for each of these. So this is really just a question about PV equals nRT. Okay, so we have PV equals nRT, and we know the pressure, the volume, and the temperature for these gases are the same. So if we're plugging in the same pressure, the same volume, and the same temperature into PV equals nRT, when we go to solve this for n, or the number of moles, because R is a constant as well here, we have four numbers that are the same. This is going to give us the same number of moles. So if we look at question 60 from the perspective of PV equals nRT, we know that the number of moles of gas in cylinder A and cylinder B will be the same. So again, because we have the same pressure, volume, and temperature of gas, this is going to give us the same number of moles of gas inside the container. And then it asks us about molecules, so of course molecules would be proportional to moles, so it's going to be the same number of moles, same number of molecules of gas in each cylinder. For question 61, what would cause this gas to behave more like an ideal gas? So if we have an ideal gas, we want the particles to be really spread apart. We don't want there to be forces of attraction between the particles, so again, being spread out more would help with that. We want them to be in random straight line motion. All right, these are some of the ideas that we are looking for with an ideal gas. So if we want the gas to behave more ideally, the two things that we could do would be to increase the temperature and decrease the pressure. All right, both of these changes would result in a gas that's behaving more ideally because the particles would be further spread apart. So if we have a temperature here that's increasing, we know that's going to cause the particles to spread apart farther. If we have a pressure here that's decreasing, the same thing. It's also going to cause the particles to spread apart farther. So both a decrease in pressure and an increase in temperature would be changes that would result in particles that are further spread apart and therefore are going to behave more ideally. Okay, and the last question here is 62. How do we calculate the volume of gas in cylinder B at STP? All right, so the STP is the key here. It tells us standard temperature and pressure, so we're looking for 273 Kelvin and a pressure of 1 atmosphere. Okay, so this is a case where we want to use the combined gas law. So we're looking for the volume here. So we know the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Okay, so if we plug into the combined gas law, and I'll take this up here so we have space, we plug into the combined gas law and we're looking for the volume at STP. At STP the pressure would be 1, the volume is our unknown, and the temperature would be 273. 273. So the conditions that we did have for cylinder A were a pressure of 1.2, a volume of 1.25, and a temperature of 293 Kelvin. So this is all we have to do for question 62, is just show a numerical setup for solving for the volume here. So if we were to actually go ahead and solve this, the easiest way would be cross multiply here and then we could solve for the volume, but we're not even going to do that because in this question you just have to show the setup. So this would all you would have to do for the setup here is just plug into the combined gas law with the numbers in the question. Alright, we'll come back in the next video with question 63. Thanks for watching.